Okay, so let's talk about standard enthalpies of formation. So we are working our way through Chapter 9 in Thermochemistry, and so far we have learned 2 ways to determine the enthalpy change in a chemical reaction. There's 3 ways that we can do it. 3 ways to determine determine the enthalpy change in a chemical reaction. And remember, enthalpy change is delta H, or you might see it called Q, heat. Okay, so the first way that we can determine the enthalpy change in a chemical reaction is experimentally, like in the lab. And you guys will do a lab on this in a few weeks where you are using a calorimeter, and you'd be using something like the specific heat or the heat capacity, or maybe even both in a chemical reaction to see how much heat was evolved or absorbed when this experiment happened. So that's one way that we use to determine the enthalpy change of a chemical reaction. Another way that we can determine the enthalpy change of a chemical reaction is Hess's law. Remember Hess's law of summation, where when you have an equation that you cannot easily experimentally determine the heat of that reaction, you can use other reactions and manipulate them to be able to add them together to ultimately come up with the equation that you're interested in. Whatever you did to those equations to add them together, you do the same thing to the enthalpy change, and that will give you the enthalpy change of your desired reaction. The third way, we're going to talk about that today, is called the standard enthalpy of formation. And the standard enthalpy of formation is abbreviated delta H and then this little subscript F. And the standard state has this little degree sign here, and that indicates that we are at standard conditions. So this little degree sign indicates standard conditions. And we'll talk about what all that means. Standard temperature, standard pressure, standard temperature of 25 degrees Celsius or 298 Kelvin, standard pressure of 1 atmosphere. So you'll see it looks something like this. Standard is the little degree, enthalpy, delta H, formation is the little F. So we would say, you would read this as delta H 0, sometimes we call that little degree sign 0, of formation. So lots of different ways to say this, all means the same thing. So, let's just do a few little definitions before we really get into it. One thing that you might see come up are something called allotropes. Allotropes are defined as different forms of an element in the same physical state. So a good example of this is carbon. Carbon solid can either be carbon that is a diamond or carbon that is graphite. So carbon graphite and carbon diamond are allotropes of each other. Another one is oxygen. So oxygen gas can either be O2, which is just oxygen, or it can be O3, which is ozone. So it has to be the same phase of matter. So both of these are a gas, just like both of these are a solid, and that's called an allotrope. We talk about allotropes because we need to talk about something called the reference form. So the reference form of an element is the most stable form of the element, both physical state and allotrope. Most stable. And this will be defined for you in tables. You'll be given information about what the reference form for different elements are. So, when we're talking about calculating enthalpy change using standard enthalpies of formation, we are calculating the enthalpy of formation. I'm going to write delta H F. So now I'm going to change this here. We're switching. So it's the enthalpy change for the formation of 1 mole of a substance from its elements in their reference forms and their standard states. Okay. Also, the delta H naught of formation of an element in its reference and standard state equals 0. So for example, the standard enthalpy of formation of liquid water. So we want to produce liquid water and we want 1 mole of it. It's the enthalpy change for the formation of 1 mole of the substance. So we just want to produce 1 mole of H2O. So usually, if I asked you to write the chemical equation for H2O, from its reference, from the elements, made up from the elements in their reference state, well, water is made up from hydrogen and oxygen. We know that hydrogen is H2 and oxygen is O2, but this isn't balanced because I have 2 hydrogens, 2 oxygens, only 1 oxygen, so I need 2 here and 2 here. So this is the balanced chemical equation that you would use to form water, but this is not what you use when you are calculating the enthalpy of change of formation, because that is defined as 1 mole. Here we have 2 moles. So now we're going to do this weird thing where you only see this in thermochemistry, where to get 1 mole of water being formed, we're going to divide this whole thing by 2. We're going to divide this 2 by 2, this 1 by 2, and this 2 by 2. And it's going to end up giving us 1 mole of hydrogen gas plus half a mole of oxygen gas gives me 1 mole of liquid water. So this is where this formula comes from. Again, this is not something that you're seeing in other types of chemistry. We would never have a fraction for a stoichiometry, a molar amount here. The only reason that we're doing this is because the enthalpy of formation is only for 1 mole of water. And to make 1 mole of water, we need half a mole of oxygen. So these standard enthalpies of formation are given You could look these up in a textbook. And the standard enthalpy of formation of liquid water, so this is standard temperature, standard pressure, reference states. Gases are the reference states for hydrogen and oxygen. Liquid is the reference state for water. The standard enthalpy of formation of liquid water is negative 285.8 kilojoules. And you don't really need to say kilojoules per mole. It's just kilojoules because it's implied that it's going to be per mole, because by definition, the enthalpy of formation is for 1 mole of water. So this is where all this is coming from. So we can calculate the standard enthalpy of the reaction using the standard enthalpy of formation of everything in the reaction. So I'm going to do that on the next page. So calculating delta H of the reaction from delta H of formation. So here's an example. I'm going to tell you that the standard enthalpy of formation for liquid methanol, so CH3OH liquid, is negative 238.7 kilojoules per mole. This would be given to you. You would look this up in a book if it wasn't given to you. The delta H of formation of gaseous methanol is negative 200.7 kilojoules per mole. So this would all be given to you. So now the question is, what is the heat of vaporization for methanol? So remember, the heat of vaporization, this is just a special enthalpy change when we go between a liquid and a gas. So whenever we're given the heats of formation of different substances, we can calculate the overall standard heat of the reaction. So let me just write out what this formula is. So it's delta H 0 of the reaction. So again, this just means at standard conditions, equals, so this is going to be a little complicated, so just hang with me, the sum of, so this little sigma letter here, this means the sum of the number of moles times the change of the standard enthalpy of formation of the products minus the sum of the number of moles times the change in the standard enthalpy of formation of the reactants. It's products minus reactants. So the enthalpy of formation of the products minus the enthalpy of formation of the reactants is going to give you the enthalpy of formation, just the enthalpy change for the overall reaction. So if I ask you for the heat of vaporization, all the heat of vaporization is delta H VAP. That's just liquid methanol going to gaseous methanol, right? That's all it is. It's the amount of energy it takes to go from a liquid to a gas. And I have these values. So let's plug that in over here. So delta H at standard conditions for the reaction, the sum of, which means if you had more than one product or reactant, you would do this and then add them together. We just have one on both sides, so we don't really need to worry about that right now. The number of moles, so I'm going to say 1 mole, and on this side it's the product. So 1 mole times, what is the enthalpy of formation of gaseous methanol? Negative 200.7 kilojoules per mole. So that's my product side. Product. Minus the sum of the number of moles, 1 mole again, times the enthalpy of formation of reactants. Well, my reactant is liquid methanol, negative 238.7 kilojoules per mole. So now this is going to tell me the heat of the reaction, which in this case happens to also be the heat of vaporization, because the heat of vaporization is just a special heat of reaction when we're changing state. So 1 times negative 200.7 minus 1 times negative 238.7, the delta, the standard enthalpy change for this reaction equals positive 38.0 kilojoules. And this is also the heat of vaporization. This is just kind of a special case. So let's look at another one. So I'm going to write it out and then we'll work through it. So it says methyl alcohol, which is the same thing as methanol right here. Methyl alcohol is toxic because liver enzymes oxidize it to formaldehyde, which can coagulate protein. So methyl alcohol, CH3OH, is toxic because liver enzymes oxidize it to formaldehyde. Which is toxic. Formaldehyde is HCHO. Which is toxic because it can coagulate proteins. That's not really important to my question. The question is calculate the delta H for the following reaction. Okay, so here's the reaction. 2 moles of methanol plus oxygen gas produces 2 moles of formaldehyde plus 2 moles of liquid water. Okay, so now I'm going to be given the standard enthalpies of formation. So these are given, or you would look them up, the standard enthalpies of formation. So for methanol, it's negative 245.9 kilojoules per mole. For formaldehyde, it's negative 150.2 kilojoules per mole. And for water, which we calculated earlier, it's negative 285.8 kilojoules per mole. So this is the information that you're given for this problem. Right away, you're probably thinking, how come I'm not given a standard enthalpy of formation of oxygen? Well, remember, we said standard enthalpy of formation of an element in its reference and standard state is 0. So you're not given the standard enthalpy of formation of oxygen because it's 0. I'll write that here just for us to remember. But there will be times, probably on your SmartWorks, where you're just not given these because they are 0. Okay, so now we're going to use this information and this formula to solve for the standard enthalpy of this reaction. So remember, it's the sum of the number of moles times the enthalpy of formation for the products. Remember, anytime you have change in, it's always final minus initial. Final is the products. This is the final conditions. Initial is the reactants. That's what you started with. So I'm going to start writing this all out. So delta H, standard delta H of the reaction is the sum of the number of moles times the standard enthalpy of formation for the products. So I'm going to put big brackets around here to indicate that we're adding these two halves together. So the number of moles of formaldehyde, 2 moles, times the standard enthalpy of formation of formaldehyde, negative 150.2 kilojoules per mole. So this is the first part, plus the number of moles times the standard enthalpy of formation of the other product, 2 moles, times negative 285.8 kilojoules per mole. So all of this right here, this is the products. So it's products minus reactants. So for reactants, it's 2 moles times negative 245.9 kilojoules per mole. And then it's going to be plus, for oxygen, it's 0, so we don't need to do anything for oxygen. So this whole thing is going to give us the standard enthalpy of the reaction. This is the product side, this is the reactant side. To get the change in something, it's always products minus reactants, final minus initial. So 2 moles of formaldehyde plus times the standard enthalpy of formation of formaldehyde plus 2 moles of water times the standard enthalpy of formation of water minus 2 moles of methanol times the standard enthalpy of formation of methanol. And when you do this, you're going to get a standard enthalpy change for the reaction of about negative 380.2 kilojoules. So this is the third and final way that we are going to be calculating enthalpies of reactions. So we did it experimentally using specific heat or heat capacity. We did it using Hess's law, and now we've done it using the standard enthalpy of formation.